Today we are taking a peek at the Unit 4 review in preparation for our upcoming test. So at the very top here, we're taking a peek at exponential growth versus decay. So one thing to remember, here's our generic form of our growth and decay equation. Now, the key with all of this, and the part that we care about, is this one, okay? The b value. If it's greater than 1, okay, it's growth. If it's between 0 and 1, it's decay, unless you have a negative exponent. Now you'll notice looking through 1 through 4 on here, you don't see one. It doesn't mean I can't put one on the test though. So remember, if there is a negative exponent, it just means that it flips that value, takes its reciprocal, and it'll make it the opposite of what you think. But for these, we're pretty straightforward. Again, my b value here is 2. 2 is greater than 1, so it's growth. Okay, again, 3 is greater than 1. It's growth. Notice it has nothing to do with what's going on the outside with my a value. That serves a different purpose. When I get to 3, you're like, dang, these are all growth. Everything's bigger than 1. Okay, there's at least one that's not. Okay, that'd be decay. So not too bad. That should be some easy ones here at the start. Okay, state the y-intercept, the shift, and the domain and range for each function. Notice I'm not graphing any of these, and I should be able to get most of my information without the calculator, but if I need it, we'll talk about what some of those options would be. Okay, on this first one, my y-intercept. Now, let me make this clear, if there's no shift, like these, okay, I can steal my y-intercept straight from there. If there are, I might have to go to the calculator to help me out with that. Okay, so I get that set. Shifts, there aren't any. That 2 is a stretch. I mean, I guess I could write stretch 2, but to me, that's not a shift, so I'm going to say none. Now, if you don't remember the domain and range of a decay, okay, remember, decay will be coming down to the right like this. That should give me a pretty good clue, but if I need a little help, as long as I'm continuing to move with this, because we've talked about with the length of the test, I can't afford to sit and stare at this for like 5 minutes, so probably would help if I actually typed in the right expression. All right, there we go. And again, I can notice a couple things. I see my y-intercept. And as I start to go along with some of these, I notice my values are getting really close to 0. If I look at the graph of it, getting really close to 0. So domain for my growth and decay functions is always going to be the same. So for all three of these, 5, 6, and 7, negative infinity to infinity for domain. My range, though, it gets really close to y equals 0. So it would go from 0, the bottom, up to infinity, which is the top. And again, if there's no shifting up or down, okay, something to remind us of, this is only going to move if I have an up or a down shift, okay? So as I continue to move across and look at some of the rest of these, now this time I have a shift, so I can't just say that it's 0, 2 for my intercept. I'm going to need a little help. So, I'm like, all right, oops, I don't need that. So I get this typed in, and again, if you're ever confused, sometimes skip that problem and then come back to it later, because we want to stay on task with this. So I look at the graph, and I notice, oh, it still looks like it's going to 0, because my shift was right 1. It didn't move up or down. Now, my y-intercept, though, again, occurs when the x value is 0. So if I go to my chart, wherever x is 0, that y value is going to be my y-intercept. Not a bad deal. And we just talked a minute ago about the shift. Okay, any shift that's up in the exponent, it's my right or left shift. One's on the end or my up or down. My domain's the same. And my range, I didn't move up or down, so it's still 0 to infinity. And I even saw that from the picture if I needed it. Okay, so there are some things the calculator can help with, and some other things that I really don't need it. So So as I kind of keep looking at these, I'm like, okay, I'm kind of seeing some patterns developing here and where I can find my info. Biggest thing to remember on this one, okay, when you have movement, okay, or shifts up there, you've got to make sure that you're using parentheses. Because if I don't, it's going to make a different value out of this. So I'll look at my chart. Okay, there's my y-intercept, 0, 1. Shifts, I have 2 of them this time. Left 2 and down 3. My domain, I already know. And my range, oh, I probably could have looked at the picture to give me an extra little assistance here. Notice it's not at 0 anymore. It's gone below the x-axis. It went down 3, just like the shift told me it would. -3 to infinity. Okay, keep making connections. But again, taking a look at these and getting a little practice doesn't hurt. Okay, move down a little, graph each function, name any transformations, any shifts, and then the domain, the range, and the end behavior. Okay, here, what's that +2 represent as far as a shift goes? Hopefully somebody at this point has said up to. Okay. Now I would hope at this point, especially if you'd flown through those ones up above, that the domain and range part for this one at least would be easy. Because again, we're looking at a classic growth and decay, so -infinity to infinity. I had an up-down shift. Okay, I went up 2, so my range went with it. And then again, end behavior is that f of x and x thing. Now again, sometimes that's easier to remember when I look at the graph, but here's my connections that we're looking at again. My domain is going to give me my x values. So one's going to be -infinity, one's going to be +infinity. My range is going to give me my f of x values. Now if you're not sure where the 2 and where the infinity goes, good way to make sure, okay, give it a quick punch into here. So 1/3 to the x. And again, I don't want the parentheses this time because the +2 is not in the exponent. So I look at the picture. And I'm like, okay, so as x is going to -infinity, as x is going to the left, as my graph is going to the left, am I approaching 2 or am I approaching infinity? Well, since I'm going up forever, it looks like I'm approaching infinity. Which then means the other one, as I go to the right, I'm approaching y = 2. Okay, I can get the graphical that way. Now as I do these other ones, these are a little different. Okay, again, transformation, same thing. Up here, what's that +2 in the exponent going to be? Left 2, okay. So again, I can go to the calculator. You're like, Harty, you never graphed on the last one. Well, why we got to worry about that? No, just kidding. Again, I can just use some points from here. Not that tough to do. And knowing that my asymptote's at 2, as long as I'm not crossing that, I'm okay. And we're going to find something similar when we do this for 9. So 1/3, again, fractions just naturally go in parentheses. It's just the right thing to do. Okay, to get my e, remember, is second in ln, second in natural log, because they're inverses, so they share the same button. And then x + 2. So let's take a look at the graph first. Oops, Harty did something wrong. Oh, I used a division sign instead of closing my parenthesis. Okay. So again, it kind of looks like a growth and decay problem. So before we even go to graphing it, okay, let's take care of some of this other stuff. My domain, still going forever right, still going forever left. My range, since I didn't move up or down at all, is still from bottom to top. My bottom value is going to approach 0, go up to infinity. My end behavior, might as well take care of that while we got the picture up, right? So, is we get this jotted down. We're like, okay, I remember from the last one, this goes with these guys. And now I got to figure out where the 0 goes. Well, it looks like I'm getting close to 0 as I'm going to the left. So y approaches 0 as x goes left. As we go left, we get close to 0. So then that means the other one should be infinity. Let's see if that makes sense. Y goes up as x goes right. Y goes up, x goes right. All right. And then I can pull my chart. Now, you're like, I don't see any whole number values, Harty. I mean, they're just like all decimally all over the place. Sometimes, especially when we deal with E, we may have to do it that way. And that's okay. Just remind yourself this graph isn't going below the y-axis. And again, as we're doing this, we're just seeing that basically there's some flexibility with these. Okay, natural logs are going to look more like logs when we're doing this, when I graph it. Now remember, with logs, we've talked about this before. This doesn't mean this graph ends here. This is going to keep going down. It just means my asymptote's right there. So if we wanted to, let's say, graph this one right away, look at the chart. Remember, oh yeah, the error messages tell me, that last error message tells me where my asymptote's at. Okay, so my asymptote is at 3. And again, that's our no cross line. My graph can't go past there. And since I've already got it up, I'm going to go ahead and just use the chart. But these are the ones, just like regular log, that I could use those base points if I wanted to get an idea. And you're like, dang, I only got 1 point. Well, that's okay. Hey, if we got to do that, we make one more point out here. Again, as long as you get a couple of points, that's okay. I won't yell or scream. But again, it doesn't stop. It just keeps going. And now I can get all the rest of my info because now I've got a picture to work with. So I'm like, okay, let's see, domain. Is that still negative infinity to infinity? No. When we go to logarithms, logarithms behave the opposite that our growth and decay do. So on these, it's my range. Forever down and a little bit less obvious, but forever up. And then my domain always goes, remember with these, we'll kind of separate them off here. If I have a left or a right shift, which I do, my domain's going to move along with it. Now, if you've been practicing these on quiz previews, on the homework, things like that, it may have taken a minute here to get back into the flow of things, but you've had some practice. It's going to click. If this is your first time, you may want to go back and look at some more of these. So again, my range goes not with the x's, but with my f of x's, my y's. So I get that in there. Then my domain does go with my x's. And again, as we're going down, looks like I'm getting really close to 3. I'm not getting close to positive infinity, that's for sure. And as I go up, I'm heading towards positive infinity. So your domain and range always connect with your end behavior values. Okay, domain with x, range with f of x, which is a fancy way of saying y, but otherwise just let the picture be your guide if you need to. Okay. So as we continue, when looking at the function, 100 times 5 to the negative x, Deanne thinks it must be growth since the b value is greater than 1. Sensible. But is she right? No. Well, why not? We talked about this earlier. It's that negative exponent. Now, explanation, there's a couple of ways you could do this. You could do it mathematically and say, hey, that 5, or 5 over 1, flips. And now since my b value is 1/5, now it's decay. Or you could just write something like the negative exponent flips b. You can't just write the negative exponent, does it? Because I can have a negative exponent and still have it be growth on something. So you've got to be specific enough to tell me what's going on. Mathematically, verbally. Don't care which, just make sure it's one of them. And again, I'm doing a lot more explanation on some of these, which kind of can slow some things down a little bit. So that's why we might have a little time issue going here, but we'll see. Okay, explain how to obtain g of x from f of x. What transformations are there? What shifts? Hopefully you've said, oh yeah, up there's left and right, so that's right, because it's the opposite of what I think. Plus 1 on the end is up or down, so in this case that's up. Simplifying expressions. Remember, we have inverses. A log of a value and the value are inverses. E and natural log are inverses. So, here, 5 and log of 5, inverses. Just leaves me with whatever's left in the exponent. Log 1/3, 27. Now remember, that means 1/3 to what power equals 27? And we've talked before about this. Fraction to whole number or whole number to fraction. I know it's going to be a negative because I have to flip it. And then really the only other question I have to ask myself is 3 to what power is 27? If you have to play with that in the calculator, you can. And you can get to the answer. Okay, now, here's your backup plan. But I'd only use this as a backup because, again, this could slow you down, and you don't want to get slowed down. Okay, we talked before about change a base. If you forget how this other part's going, you always can do the log of your of value, the physically larger number on the right, divided by the log of your base. Okay, you can get the number that way too. But you can't flip them around. It has to be in that order or it doesn't go well. And just like we had it on number 16, okay, whole number to fraction, same deal. I know it's negative because it's flipping. 10 to what power gets me to 100? 2, I'm good. Here, 5 to what power equals 5? Well, duh, anything to the first power is itself. And then the last one, 2 to what power is 1,024? I'm assuming most of you are going to have to play around in the calculator for a bit with that one. But that one would be 10. Again, we kind of just keep rolling with that. Okay, now here's my hint on 20 and 21. Rewrite the following into logarithmic or exponential form. You have the other form sitting here. I'm trying to turn this into this, or this back into this. So I'm going, okay, that's my base. So again, we've got our base number here. And we always had talked about how our exponent is on the other side of the equals, because we'd always said base, exponent, answer. And so then my answer is x. 5 to the 4th power equals x. Okay, I'm good. And then I use the other one and I just go backwards. I go, okay, that's my base. There's my exponent. There's my answer. And for some of you, doing this one may be easier, so maybe you do this one first and then work your way back to this one when you have an exact matching example, but that choice is yours. Okay, expanding expressions, reminders. Multiply becomes add. Divide becomes subtract. And exponents become coefficients. And I basically want to go somewhat in that order. Okay, and kind of take my time. So here I notice, okay, 3 times x, that's a multiply. So I take my log 2, and wherever the multiplication dot would be is where I start over again. No exponents, no dividing, that's done. But I have to have that log base 2 in each one. I don't have a choice. I'm just saying, oh, I'm just going to write it once. Can't do that. Now, the second one, I have choices. Because I see a multiply here and I see a divide. How do I make up my mind? Well, maybe I just kind of work left to right. And I'm like, okay, so the natural log of 10 plus the natural log of x. So now that we've taken our natural log, since it was multiplied, turn it into add. I normally at this point, since there's a fraction, I'm going to put parentheses around this. Even though we normally look at them left to right, it's something that just is a smart thing to do. And then the division sign becomes a subtraction, and I do that with the natural log of 3, and I've taken care of my multiplication and my division, and I'm fully expanded. Now the last one, it's the mother lode. We get a little of everything here. So here again, I'm going to do this one in steps. So here, if I'm just looking at the numerator here at the start, I'd have log of x to the negative third plus log of y to the fourth. Okay, there's going to be more there to do, but we'll come back. And then in the denominator, I've got log of 4, because again, there's multiplication dot there, plus the log of y. But like I said, I'm not done yet. Because now I look up in the numerator and I notice I have exponents, which are going to become coefficients. So that would be negative 3 log x plus 4 log y. And again, since I see the fraction there, the divide, I'm going to put that in parentheses. Because this next part then will be minus to take care of the division bar. And I don't see anything else I have to do here. There's no other exponents. This 4 isn't coming to the front. Okay, not an exponent. So I'm just going to rewrite that. And I'm set. Just take it in small pieces. You'll be okay with those. So then our next part says to condense. Now, condense basically just means I'm doing all these things backwards. Coefficients become exponents, subtract becomes divide, add becomes multiply. So, and we're also going to take them in the reverse order. So for instance here, any coefficients I see are going to become exponents right away, because that's going to be the easiest way to run this. So I get that written down. Then subtraction becomes division. Because again, condense the expression. Sometimes it's even said into a single logarithm. So I want one log at the end. And I'm going to have x to the 7th. The minus becomes divide. Okay, one term. Not ln x to the 7th over ln y, just one term, one logarithm. And I do the same thing as I work through all of these. Okay, coefficients become exponents. If you want to try doing multiple steps at a time, you can, but I think a lot of times we run into a lot more errors going that route. Then here the plus becomes multiply. Single logarithm. 5y to the 1/2. Because again, the 1/2 only goes on my y, not the 5. And I'm good. And then finally, again here, okay, this time we have more coefficients to deal with. So we've got 9 to the 1/2. We've got 4 to the 3rd. Then we have our log 8 that's still going to be the way it is. Now, I'll always have people ask me, do I need to simplify this? I mean, 9 to the 1/2 is like the square root of 9. Do I have to make that 3? I don't really care because I'm watching more of you condensing and watching that than I am those values. So if you want to reduce that, you could. You're like, well, now what do I do? Typically, I work left to right. So I go, okay, so this is going to be log, plus becomes multiply, and then the minus becomes divide. I'm fine if you leave it that way. But if you want to multiply it out and see if you can simplify it more, there's nothing wrong with that. But that's the format I'd be looking for right there. Find the inverse of the following. Inverses, reminder. Those two values right there are going to switch. We get those flopped. And then again, my whole goal here is to get the y by itself, to solve for y. Well, that log 4 is in the way, but unfortunately, I can't just divide both sides by log base 4. We have to exponentiate. So taking a quick peek back up here, again, to get rid of a logarithm, we can use its base value. So down here, for us, that means we're going to use that base value 4 to exponentiate. But be careful when you write the answer. Exponentiate, base, exponent, 4 to the x power. Not 4 times x. You put 4 times x, it's not correct. So that's the only step. That's it. We're done. Switch them, exponentiate, we're good. Okay. Solve the equation. Reminders here again. If you have a base number you are trying to get rid of, you can use the log of that value to get the 5 out of there. I cannot divide by 5. It is not 5 times x, it's 5 to the x power. And like we did another time on the front, when I get to this, and again that's 5, if I'm going to my calculator, which you should, I'm going to do log of 16 divided by a log of 5. I'm going to do what's called change of base. So log 16 divided by log 5. Hey, and normally on one like this, probably going to go to the thousandths place. So that's what I'll do. But you've got to keep them in that order when you do it. Now, we have lots of tools in the toolbox, so there may be several different ways we're going to look at this. Like here, I want to get rid of the log. Okay, so it's the exact opposite of this. I'm going to exponentiate with my 5, because then the 5s can't. The log 5 and the 5 are inverses. And be careful. 5 to the 4th power, not 5 times 4. And I can get my answer for that. And I just keep working through these. I'm like, okay, let's see. I want to get to that 8x. What do I have to do to get rid of natural log? I use e. And just a reminder, when you're using e, let me pull that up here. I'm going to find e by taking second natural log. Okay, don't type in the alphabet and hit that e. That won't help me. That's the letter. This is a value. So we're going to e to the 4th. And then now we're back to just plain old algebra. What am I going to do to get x by itself? Yeah, I'm going to divide by 8. And I'm set. Okay, but again, that's only when I can happen to use a singular log in one place. Well, what happens here? Because I can't do log 4, because the 16 wouldn't cancel. I can't do log 16 here because the 4 wouldn't cancel. What do I do? We have a plan here. We have to mess with our bases, and we've done this some. Okay. Can I take 4 to some power to get to 16? I sure can. I can take 4 to the 2nd power. So whenever I see these, I'm going to look at that larger value and say, hey, can I take the smaller value to some power to get to it? Because now I can use my log of base 4 as an inverse. And whatever is left up in the exponents, over here I've got the 2 left from here still, plus the 2x minus 3. And now I just solved this like I would any equation. I'd minus my 4x over. And again here, since we're multiplying by x, multiplying by negative 3, we would divide both sides by negative 3 to get to my solution. And again, I know there's several different things going, but again, the more practice you have, the better off you're going to be. Now here I got a couple of questions. First, I don't see a base number with my log on 33. What's that going to be? It's going to be 10, but I can't exponentiate yet. Well, why? Because my log has this 2 in front that's sticking me. So, since I'm multiplying by 2, I'd divide by 2, get that 2 out of there. And now I can go through, because the next thing that's in my way of getting to the 44 is that log base 10. So I exponentiate. Need a little calculator help here. I don't know 10 to the 1.5 off the top of my head. And then we'll just add the 44. And we're ready to go. Okay, so again, we're trying to get a log of a base out of there. We exponentiate with that base value. If it's the base value we're trying to get, we take the log of that value to get it out. And then, best situation ever. This should be like the easiest question on here. If I had the same log on both sides of my equation, I can exponentiate with that right away and just have this left. I'd minus my 2x over and divide by 2. Nicely played. And I start to see all of this. Now again, always looking to see where is my x term at and what do I have to get out of the way to get there. Here, okay, this is just a positive 1 here. I'm not multiplying it, so if it's just sitting there, I've got to minus that 1. Okay. I still don't have my natural log where I can get it out of the way with e yet. So since I'm multiplying it, notice there's no plus or minus in between these. So that's how I know it's multiplying, that I have to divide. And then now finally I've made it to where the natural log's the only thing left in my way, and its inverse is e. And whatever, and no, it's not time to go. Okay, and we're set. So that kind of gets us away from the log stuff here for a bit, because we got some applications that we need to do. And again, if you need to go back and look at some of the log stuff, that's stuff we were just doing last week, so it'll be fairly easy, I would hope, to be able to find some of that to look at. Okay, reminder. On these type of problems, I will give you the expression. Don't get creative, okay? Population of a city. Now let's rewind for a second here. Okay, reminders again. A is what I start with. Y is what I end with. And R is my rate as a decimal. If you don't know how to do it, just take whatever percentage they give you, divide it by 100. That'll give you the rate as a decimal. So for instance, in our first one, population of a city in 1985 was 1,275,390. That's my A value. The population was growing, adding, at a rate of about 4% per decade. Again, if you don't know what the decimal is, just take 4 and divide it by 100. That would be my rate. And since it's growing, it's plus. Predict the population of the city in 2005. Now, be careful. A lot of you are going to be tempted to use 20 here. You're like, well, it's 20 years later, 1985, 2005. Why wouldn't I use 20? Read carefully. Per decade, per every 10-year period. Well, if it's 20 years, how many 10-year periods are in there? 2 of them are. Okay, I gotta be careful. I can do everything else right and have that go bad. Now, do I have to use y equals this time? No. Why? Because I'm not looking for several values. I'm looking for one very specific one. Could I use the y equals? Sure. I just get the same answer all the way down. But here, I'm just going to go ahead and type it in and get my value. Now again, we're talking about people here. Do not give me 82 hundredths of a person. That's gross. Okay? People are people. They're a whole, one way or another. All right. 37. The value of a new car purchased for $18,500, there's my A, decreases minus by 8% per year. What's the value of the car after 4 years? But I also notice when I look down below, how many years until it's worth $10,000? So I have a what if question. So this time I am going to go to the y equals. And I'm going to type in my beginning value. And the 1 minus the percentage to the x, so I can have several years open as an option to me. So I look at the chart. Okay, after 4 years, it's about 13,253. There may be some cents involved, but that's okay. When's the car going to be worth 10? Find that first year that it goes below that. Okay, if you wrote 8 years, that'd be okay. If you wrote 7 to 8 years, still not time to go, that's fine. Okay? I'm not looking for a absolute definitive. After 7 years, it's still going to be worth a little more than 10, though. So I'd have to say up to 8 if I was going to go that route. Oh, we're getting there. We're getting there. All right, suppose you deposit your paycheck in an account that pays 3.5% compounded continuously. Again, you can't pick and choose your equations. You have to use that one to get the exact right answer. Find out how long until the balance triples. You're like, well, wait a minute, I don't even know how much money I made. Okay, when you don't, you get flexibility. You can say what it is. I'm going to go ahead, I'm going to use 1,000. E to the RT. How long until the balance triples? 3 times as much as whatever you had to start with. Now again, I have options here. Okay? So here's kind of what I'm thinking, because again, I'm not looking for down to the day here with anything. So I look and I'm like, okay. One of the ways we've looked at it, if we're not going to go the algebra route, is to look in my chart and go down until we crack that 3,000 mark. Okay, so about 32 years. Additionally, I could solve this algebraically by looking at this as my equation and saying, okay, I'm going to divide both sides by 1,000. I want to get that out of there. I'm going to take the natural log to get rid of e. So I'll scoot this over a little. And then I could divide that by 0.035. And again, over 31 years decimally. And you kind of see where I could get my answer either way. So I don't care which route you go. Okay? They'll both get you to approximately the same answer, 31, 32 years, somewhere in there. Okay? Growth of a stock's value after its purchase in 1985 can be represented by the equation A equals 501.04 to the T. What's the value of the stock in 1985? That's my base year. That's when T equals 0. And whenever T equals 0, you're just going to get the initial price back. Excuse me. What is the annual rate percentage of growth? Well, they give it to me as a decimal to get it back to a percent. Before, when we were going the other way, we divided by 100. Well, now we're going to multiply. And 0.04 times 100 would be 4, which is 4%, and we're set. Now back to regular problems. We're going to invest some money in an account paying 4.5% interest compounded monthly. Find the balance after 10 years. Okay, So principal, my rate, again, got to make the change. Compounded monthly, how long does that word after compounded happen in a year? That'd be 12. Scooch over a little here. And then 12 times 10, because it's n times t, just like it is over here. So I pop this in. I don't need the chart because I'm only being asked for one value. Get that in there. Now, let's start to look at this for a minute. Now, if I typed that in, right now I see almost $1.7 million. Now, does that make sense? $8,500 for 10 years at 4.5% interest. Am I going to get that? No. What went wrong? Well, you typed too fast. You didn't put the divide number in here. Okay, but those are the type things, again, to think about. If you get a number that's absolutely ridiculous, you need to go back and say, did I type something wrong in the calculator? Was I going too fast? Did I hit, multiply instead of divide somewhere? What's the deal? That's much more reasonable. A little over 13,000, yeah, that could happen. But probably not over $1 million. Probably doesn't make a lot of sense then. How many years will it take for an account to double if its value collects 5% interest compounded quarterly? Use the formula from 40. Okay, again, I get to make it up. So let's say I had $1,000. How long does it take to double? That'd be 2,000. 1 plus my rate quarterly. And I don't know what the value is for t because that's what I'm trying to find. Now again, you can use either of the methods we talked about up above. In our case, I have a feeling a lot of you are going to go this way, but maybe some of you will do it algebraically because they both will get you to the right place. Let's see if I can actually type it in correctly this time. Okay, and if I'm going this route, remember, I'm looking to see how long it's going to take for that to make it to 2,000. So again, how many years? Like 13 to 14, but if you're only going to choose one, you choose the one after you've hit the 2,000. And then you're set. All right, application time. Oh, application. All right, money in two different accounts. They tell us the amount, they tell us the interest. They give us expressions for both. How many years will it take for the two accounts to have the same balance? Okay, here's what we got to fight here. And I'll get this in the middle so we can actually see how this is working. And I'm going to try to get these typed in quickly so we can make sure we got time to touch on everything. Okay. So I get these into my chart. Let me get back up to the top here. Okay, how many years will it take for them to have the same balance? Now, does that mean you're going to see the exact same number in both columns? No. Here's what that means. When does y2 get bigger than y1? Because you notice at the start, the first column is bigger. Now, as I start to scroll down, at some point, the second column is going to get bigger. And there it is. Okay, it took until I got to 12. So sometime around 11 to 12 years, because 11, the second one's less, 12, it's bigger. So somewhere in that period, this is going to happen. And then the question we've asked on a lot of quizzes, which account's a better long-term investment? So to me, B, because after 12 years, I get more money. Again, the key here is long-term. If I asked you short-term investment, it'd be A, because you'd make more money short-term. And that's going to be the general theme that I get in the second one as well. Okay. again, 2 job offers. One $60,000 with an $1,800 raise. The other $50,000 with an 8% raise. Give you the expressions again. So, similar to what we did in the last one, what we're going to do is we're going to get both of these in here. Oops, I almost lost my X. That would have been a problem. So that's my first one here, busy bee. And then my second one, and again, just like before, we're going to start from the beginning. Uh-oh. Oh, what do we do? Okay, so I look and I'm like, okay, the first column's bigger than the second. Gotcha. Okay, how many years later is the second one going to overtake the first one? So I look, wow, that didn't take long. We're in year 4 and the second column's already bigger. So, 4 years till it gets bigger. So again, which offers best? It depends. If I stay over 4 years, Bugsy is better, but if you're like, well, I'm only going to stay a couple of years because I'm going to be moving, okay, then maybe the other one's a better idea. But explain, don't just say, Bugsy's better because it's money. Well, no, like they both are offering you money. We got to explain, which one's better and why that is. All right, home stretch. Yay, multiple choice on the end. Okay, which type of function is this for e to the negative 3x? Now, if you look at that and you're like, I don't remember what this is. Well, one thing I'll be able to tell you is it's going to be a or d because it's not linear. It's not just like 4x. It's not quadratic. It doesn't have something squared. So if you're not sure, what option do you have? I can always go to the calculator and just look at it if I really want to. Okay, and I'm always about trying to find ways to simplify things for you guys. So if you look at the graph, looks like it's coming down. Looks like decay to me. Okay, not a hard thing to look at. Okay, what's the asymptote of the graph? Alpha of x equals 4 to the x minus 2. Okay, again, we're looking at a growth decay where we're looking at up-down shifts. Well, this one goes down 2, so instead of being at 0, which it typically would be, it moves down 2 along with it. Again, I could punch it in the calculator and look at it and look for the error message too if I have time. Okay, which of the following is equivalent? Basically, it's asking us to expand. So the times here becomes plus. And then minus for the division. And again, the times down here becomes plus. Now, you start to look at that and you're like, I don't see that. Well, because these people, I guess, decided they weren't going to expand as much. So you're like, okay, well, the divide becomes minus. It's not divide. That ain't right. 1/2, there's no square roots. And for this to be plus, they'd have to be multiplied together, but it's divide. So it has to be this one. So I kind of pay attention to what's being offered. And then finally, what's the value of negative 3 times 2 to the x when x equals 0? I can plug it in the calculator, or anything to the 0 power just equals 1. Negative 3 times 1 is negative 3. Okay, yes, this took an entire class period to do. But remember, your test is only 2/3 as long, so you have time, because you're not going to be having to explain every step to me like I'm doing on this. Look things over. Grab another review if you need to. Go back over your notes. Write a few problems down. Do something, but just be ready for this, because again, when the hour's over tomorrow, you are done. So pace yourself well. You've got this.